Hey everyone, this is a video of working through problem set 35 about enthalpy. You can see how it breaks down there, delta H is of reaction, delta H is formation, Hess's law, and bond energy. Our goal here is to gain an understanding of what enthalpy is. And let's see, in this problem set we'll do a little bit about how to calculate enthalpy of a reaction. And so let's get started. So let's talk about what exactly enthalpy is. Enthalpy refers to the total energy of the system. So previously we've talked about energy, but that was specifically talking about internal energy, which is like the energy that has to do with the actual molecules that exist in a system. So the energy inherent in those molecules, I guess is a good way to say it. Enthalpy now, which is H, is going to equal that internal energy, but then we also add on to it PV, which basically what that means is it's the internal energy of the system as well as the energy that's required in order for that system to maintain its shape in space, I guess is a good way to say it. So when a system expands, it performs work, and it kind of pushes its surroundings away from it. So the energy required to maintain that pushing of the surroundings away, that's kind of what this PV accounts for. So that's what enthalpy is, the total energy, which is going to be the internal energy, E, and then that pressure and volume factor that gets added on there. So then we could write that delta H is equal to delta E plus delta PV, those deltas being changes, of course, and we'll talk about that. We'll talk about that in a minute. So, talked about the difference between internal energy and enthalpy. We kind of talked about that already. So the internal energy is just the potential and kinetic energy of a system, again having to do with just the molecules that exist there. And then this also takes in, enthalpy also takes into account the energy required to displace its surroundings, or displace the environment is a good way to put it. Cool, and then when does delta H equal Q? Okay, this matters for us. So let's talk about this. If I have delta H equals delta E plus delta PV, I could break that up into delta H equals delta E plus P delta V plus V delta P. So this is the chain rule, essentially distributing a change in something. You distribute it to the first thing, and then you distribute it to the second thing, and you add them together. So that's all I'm doing there. That's just kind of calculus. You don't really need to worry about that, but these two things are equivalent to each other. All right, so what we're going to assume next, we're going to assume that pressure is constant. If pressure is constant, that V delta P is 0, because delta P, the change in pressure, if pressure is constant, is 0. So that leaves me with delta H equals delta E plus P delta V. And then I can say, well, I know that delta E, write this up here, delta E equals Q plus W. And I also know that W equals negative P delta V. Right, so if you're confused about that, you can go back and look at videos about work. What problem set is that? Problem set 32, we talked about that. But so energy is Q plus W, which is the same as Q minus P delta V. So then I could replace this energy right here with this term right here. That's what I'm going to do. And that gives me delta H equals Q minus P delta V plus P delta V. This part is still there. Well, you can see hopefully delta H equals Q minus P delta V plus P delta V is just delta H equals Q. And so the question is, when is that true? When does delta H equals Q? Well, what's the one assumption that we made? The one assumption we made was pressure is constant. So the answer to this question would be when pressure is constant. And you don't need to worry about determining when pressure is constant, because in Chem 105 pressure is always constant. So you are in good shape there. All right, so let's keep going. So adding Drano, well, let me actually talk about this a little bit more. Delta H being equal to Q. What does that mean? That means we said that enthalpy refers to the total energy of a system. So change in enthalpy will refer to the total change in energy of a system. When we say that delta H equals Q, what we're saying is that the only way to change the total energy of a system is through heat. Because the two ways we talk about are heat and work, but if pressure is constant, this work term cancels out. But basically what we're saying is that when pressure is constant, the total change in energy or enthalpy of a system is equal to the heat that's transferred. Okay, that's what we mean. Enthalpy just refers to heat. You don't have to think of it as referring to total energy and pressure is constant. You can just think of it as referring to heat. All right, so let's talk about this. Adding Drano to a clogged sink causes the drain pipe to get warm. What is the sign of delta H when Drano dissolves in water? Okay, so let's talk about what the signs of delta H mean in general. Okay, so if I have a positive delta H, that means that heat is being added to my system. If I have a negative delta H, that means heat's being removed from my system or heat's leaving my system. So I've got a drain, it's clogged, I put Drano down it, okay, and the pipe gets warm. Drain pipe gets warm. Well, is the Drano dissolving? So this is the system. Drano dissolves in water. That's my system. Okay. That means my drain pipe is what? My drain pipe is not my system, it's my surroundings. So my surroundings are getting warm. That means my system must be releasing energy, which means delta H is going to be negative. Okay, because it's releasing that heat, which is getting absorbed by the pipe, which is why the pipe gets warm. Okay, breaking the small pouch of water inside a chemical cold pack containing ammonium nitrate activates the pack, which is used by sports trainers for injured athletes. What is the sign of delta H for the process taking place in the cold pack? Does delta H equal Q in this process? Okay, so we break the cold pack. The ammonium nitrate activates, and okay, the pack gets cold, right? So what's the delta H for the process taking place inside the cold pack? Well, the solution in there gets cold. What does that mean? That means that heat must be being removed from that solution when the ammonium nitrate dissolves. Okay, so the ammonium nitrate dissolves, it sucks heat out of the water in the pack, so the pack gets cold. Well, that means that the delta H must be positive if it made that surrounding water get colder. All right, what is the sign for delta H of the process taking place? Again, that's positive. Does delta H equal Q in this process? Delta H does equal Q because we're not changing the pressure in the universe when that's going on. Because pressure is not changing, delta H equals Q. All right, calculate delta E and delta H for the following situations. So we've got a gas that absorbs 25 kilojoules of heat. Cool, so Q equals, it absorbs 25, so positive 25 kilojoules. Okay, again, and expands 25 liters, so that it's expanding, so my change in volume is going to be positive 25 liters against 1 atmosphere. We're looking to calculate delta H, and we're looking to calculate Q. We know delta H equals Q, change in energy equals Q plus W. This again is back on problem set 32. We did some of this, which is the same as Q minus P delta V. Do we have all those values? Absolutely. Q, P, delta V. So delta E is going to equal 25 kilojoules minus 1 atmosphere times 25 liters. Okay, hopefully you recognize right now there's a problem here. We've got kilojoules and we're subtracting liters times atmospheres. Okay, if you're trying to do addition or subtraction, your units need to be exactly the same. So what I'm going to do is I'm going to convert this liter atmospheres here into joules and then into kilojoules. Okay, so what does that look like? I can just go like this. I can say I know that 1 liter atmosphere is 101.3 joules, and then I know there's 1,000 joules in 1 kilojoule. Okay, if the way that I wrote it out this way doesn't really make sense, basically you can just calculate the work in liter atmospheres and convert it to kilojoules. That's all I'm doing. All right, so when I plug all these numbers in, I got my delta E equals 22.47 kilojoules. And that should be positive. Oh, and then I need to calculate delta H. Well, pressure's constant. What does that tell me? That means delta H equals Q. Since I already know that Q is 25 kilojoules, delta H must be 25 kilojoules. Okay. B, a sample of gas releases 9.2 kilojoules of heat, so Q is going to equal negative 9.2 kilojoules. It also is compressed from 30 liters to 5 liters, so my delta V is going to equal 5 liters minus 30 liters, which equals negative 25 liters, and the pressure is 3 atmospheres. Cool, so let's do the exact same thing. We've got, this time, why don't I calculate the work and convert it to kilojoules before I calculate energy? So I know that my work is going to equal negative P delta V, which is going to be 3 times negative 25, which is going to be 75 liter atmospheres. Then I'm going to take that 75 liter atmospheres and convert it and say 1 liter atmosphere equals 101.3 joules. And then I know there's 1,000 joules in 1 kilojoule. So 75 times 101.3 divided by 1,000, that got me 7.5975 kilojoules of work. And so then I say, I know that my delta E is going to be Q plus W, which is negative 9.2 plus 7.6. And that gives me delta E equals negative 1.6 kilojoules. And then my enthalpy again is just equal to my Q. And let's keep going. Gas reaction releases 150 kilojoules of heat. Q is going to be negative 150 because again it's being released, so it's got to be negative. Releases enough gaseous product to expand 275 liters. So my delta volume equals positive 275 liters because it's expanding. Oh, to expand to 275 from 5. So it's going to be 275 minus 5 liters. So 270 liters is my change in volume. And my pressure is 2.5 atmospheres. Okay, so same thing. Delta E equals Q plus W and then I'm just going to convert that. I know that 1 liter atmosphere is 101.3 joules. I know that 1,000 joules in 1 kilojoule. Sorry, I should have done Q minus P delta V. Right, and that gives me a change in energy of negative 218 kilojoules, and my delta H is equal to Q. All right, because we haven't had enough of it, let's do another one. Reaction that absorbs 75 kilojoules, so Q is going to be positive 75 kilojoules because that's absorbed. releases enough gaseous product to expand 150 liters, so they're just giving us the delta V here. It's positive 150 liters against an external pressure of 5 atmospheres. Delta E equals Q minus P delta V. Convert that. Okay. And I get delta E equals negative 0.975 kilojoules. I also get that delta H equals 75 kilojoules. Cool. So that is calculating energy and enthalpy given heat and work information. All right, so what are delta H of vaporization, fusion, reaction, formation? How do they differ? Okay, hopefully this is pretty straightforward. So delta H is enthalpy. It just refers to a heat change through a process, and the subscript tells you the process. So delta H of vaporization is for vaporizing something. It's the heat needed to vaporize something. Usually, all of these will be written in kilojoules per mole. So the heat required to do that process for 1 mole of something. So delta H of vaporization for water is 40.7 kilojoules per mole, meaning it takes 40.7 kilojoules to vaporize 1 mole of water. So then delta H of fusion. Fusion is the weird word that we use for melting. We're talking about thermodynamics. So this is the heat required to melt 1 mole. Delta H reaction is more general, right? That just means for a certain reaction, what's the heat change per mole? And that would be per mole of reaction. And then delta H formation, that's specifically talking about a formation reaction, which we'll talk about on problem set 36. But that would be the change in enthalpy, or the heat required to form 1 mole of something from its pure elements. So don't get these mixed up. They don't come from different equations. You're going to use them all exactly the same. It's just that they're referring to different processes, but that doesn't really matter in the way that we use them. All right, what's the difference between, wow, I don't know what those are. Let me look and find out what those are supposed to say. So this is supposed to say delta H naught of reaction and delta H of reaction. All right, so delta H naught, that little circle, pronounced naught, represents standard state. Okay, so this is standard state. Okay, standard state. We use standard state standard state or standard conditions. We use standard state when we talked about gases. For gases, standard state was 0 Celsius and 1 atmosphere. It's kind of annoying, but in thermodynamics, standard state is 25 degrees Celsius and 1 atmosphere. Don't ask me why, but that's what it is. Delta H reaction is more general. It could be at any conditions. All right, explain Hess's law in your own words and describe why/how it's so useful. Okay, Hess's law. Hess's law says that if I have reactants and I have products and I am trying to find the delta H to get from the reactants to the products, but I don't know the delta H to get from the reactions to the products. Hess's law then says, well, let's say that I know a reaction that gets me from my reactants to some species, and then another reaction that gets me from those species to these species, another reaction that gets me from B to my products. Well, this reaction has a delta H, this reaction has a delta H, and this reaction has a delta H. I'll call them 1, 2, and 3. And if those 3 reactions get me from reactants to products, then the delta H of my reaction is just going to be the delta H's of my component reactions added together. In essence, if I have multiple reactions or component reactions that add together to make my total reaction, then the delta H's of my component reactions add together to give the delta H of my total reaction. Okay, this is an example of the state function. I don't care how I get from reactants to products. As long as I get from reactants to products, my delta H will be the same, because delta H is a state function. It's not path dependent. It just cares about where you're at. So that's a state function property. So we're going to use Hess's law a few questions from now. But first, we're going to use the information to the right to answer the following question. What is the enthalpy change? Okay, remember, that's just like saying what's the heat change when 100 grams of ice at negative 30 degrees Celsius is warmed to form water at 50 degrees Celsius. All right, so we're going to be calculating a Q for this transition for water. So if you remember, this is a heat curve for water. Basically, as I add, so I'm down here, I'm a solid. As I add heat, my solid heats up until it gets to here, which is 0 degrees, which is the melting point, at which point the heat that I add just goes into melting, so the temperature doesn't increase. Then once I've got all liquid and I add heat, the temperature increases again until I get to the boiling point, at which point the heat just goes into boiling, and once I'm all vapor, I can heat up again, or the temperature can increase again. So in this problem, we've got 100 grams of ice. We're at negative 30 degrees Celsius, so we're starting somewhere down here, and we want to form water at 50, so we're ending right here. Well, each of these lines requires a different equation to calculate heat. If I am changing temperature, then I'm going to calculate my heat by using a specific heat, MC delta T. So that's going to be true there and here. If I'm not changing temperature, in this case I'm doing a phase change, I'm going to use an N delta H. So if I want to calculate the heat from this point to this point, I'm going to do it in 3 steps. 1, 2, 3. Then I'm going to add all those together to give me my total heat. So Q1 is going to be heating up the ice. When I calculate Q1, I got the mass of my ice, the specific heat of my ice, and the change in temperature of my ice. And that's going to be, I've got 100 grams. Wow. 100 grams. Specific heat of ice, 2.03 joules per gram Kelvin. And then my change in temperature, well, I'm starting at negative 30. And where am I ending at? I'm heating up my ice until it's at 0. So my final is 0. And final minus initial is going to be plus 30. Okay, now I left these in Celsius. That might be confusing because that's in Kelvin. But because we're dealing with a change in temperature, I could easily change this to Kelvin, but what am I going to get? I'm going to get 273 plus, so this is minus negative 30. So I would get 273 minus negative 30 plus 273 will give me 243. Okay, and you'll notice the difference between 0 and negative 30 is a change of 30, right? And the difference between 273 and 243 is a change in 30. Okay, and so it doesn't really matter if you convert it to Kelvin, so that's why I did it. Okay, but this is going to give me my Q1, which is 2.03 times 30, 6090 joules. Okay, Q2 is going to be vaporizing this middle step, not vaporizing, melting my ice. So I'm going to use an N delta H, and this is technically delta H of fusion because I'm melting. So I need moles of my thing. I've got 100 grams, but I need to get it into moles. Why? Well, my delta H of fusion is in moles. So I'm just going to say I know that 1 mole of water is 18 grams. So now I'm in moles. Got to multiply that by my 6.01 kilojoules per mole, and that gives me 33.39 kilojoules. All right, and now I can get my Q3, which is now heating up my liquid water. So because I'm just heating it up, I'm going to use an MC delta T. But I need the specific heat of water, liquid water. What's my change in temperature? Well, I'm going up to 50. My final is 50. My initial is from the melting point, so that's 0. That gives me 2,920 joules. So now I just need to add up my Q's. Okay. What's the problem though? Well, I've got a Q in joules, one in kilojoules, and the other in joules. If I want to add them up, I need them all to be in the exact same unit, so I'm just going to quickly convert them. So I'm going to have 6.09 kilojoules plus 33.39 kilojoules plus 20.92 kilojoules. Could I have converted them all to joules? Sure. Doesn't matter as long as they're the same. And when I add them all up, I'm going to get that my total heat or total enthalpy change, so I could say delta H equals Q, which equals 60.4 kilojoules. Okay, so what is the enthalpy change when 200 grams of steam at 150 degrees C is cooled to ice at -50? Okay, so if I were to draw my heating curve, okay, where am I starting? I've got steam. Remember, boiling point is 100. Melting point is 0. I've got steam at 150, so I'm somewhere up here. And I'm cooling down to ice at -50, somewhere down there. So how many steps do I have? I have to heat up my ice, or I guess I'm starting at steam, right? So I have to cool down my steam to the boiling point, at which point it condenses, and then I got to cool down my liquid to the freezing point, at which point it freezes, and then I got to cool down my ice. So I'm going to have Q1, sorry, I should go the way we're going. Q1, Q2, Q3, Q4, Q5. So let's do it. All right, Q1, I'm cooling down my steam, so I'm going to use an MC delta T. I've got 200 grams. The heat capacity of steam is 1.84. And my temperature change, well, I'm starting at 150, I'm ending at 100. So 100 minus 150. I'm going to set all these up, and then I will plug them all into my calculator at the end. Okay, Q2, I am condensing my steam into water. So I've got 200 grams, but my delta H of vaporization is in moles, so I'm going to just change it to moles. And the delta H of vaporization is 40.67 kilojoules per mole, but am I vaporizing this stuff? No, I'm not. I'm condensing it. So to vaporize, I have to put in 40.67 kilojoules per mole. If I'm condensing, that means it's going to release 40.67 kilojoules per mole. So my actual delta H here is negative 40.67 kilojoules per mole. Okay, Q3, I'm just cooling down my water, my liquid water. technically these are written in Kelvin, doesn't matter again, like I said before. Final is 0, my initial is 100. Q4, I am freezing. So I'm going to, again, use my delta H of fusion, but I need to use the negative value. Then Q5 is just me making my ice even colder. So I need the specific heat of ice, 2.03. And I'm finishing, my final is -50, my initial is 0. Okay, let's plug all this into my calculator. Now you'll notice I'm getting negative values for all of these numbers, whereas in the problem before I was getting positive values. That makes sense, because the problem before I was taking a low energy system like ice and converting it to a higher energy system like liquid water. Here I'm taking a high energy system, steam, and I'm converting it to a lower energy system. Then what that means is that heat must be being released from it, so all of these Q's are going to be negative. Let me just make sure those numbers are right. Yep. Yes. Okay. So now if I want the total heat, I just had to add all of those up. I'm going to again change them to kilojoules on the fly here. So -118.4 plus, nope. Did I get the right answer? Yes. I get that my delta H, which is just heat, is -641.05. So hopefully this isn't confusing. I'm calculating the total delta H, the total enthalpy change, which is the same as the total heat change. But for some of these heats, I used delta H's in order to get the heat. But then I say, well, delta H is equal to heat. Well, the total enthalpy is equal to the total heat, but these delta H's are like a unit enthalpy. They tell me how much heat is involved to change 1 mole of something. Okay, so they're like a theoretical value, if that makes sense, versus this H, which is the actual total heat that goes down. This is a theoretical value that we use to, by multiplying it by moles, we can figure out the heat involved with one step in the process. All right. Let's keep going. Okay. Use the information about water above to answer the following questions. All right. Refrigerators and freezers remove heat from food by evaporating volatile liquids such as CF4 and then recomposing or recompressing the vapor back into liquid. Cool. Calculate what mass of water at 0 degrees can be converted into ice at 0 degrees. So temperature is not changing. All we're doing is freezing it. When 100 grams of CF4 evaporates. Okay, so CF4 is going to evaporate. Okay? Evaporation is an endothermic process. You have to put heat into it. So we're saying, well, what if we make those two things happen right next to each other? We've got CF4 evaporating right next to water that's at 0 degrees. Well, if the CF4 wants to evaporate, excuse me. If the CF4 wants to evaporate, it needs to extract heat from something. If it's right close to the water, then it can take the heat out of the water, which results in the water freezing because it loses heat. So that's is very close to what happens in your freezer. You've got coils that have something like CF4 that's evaporating in those coils in your refrigerator, and they take, or refrigerator or freezer, and they take the heat out of the air in your freezer, and that makes your freezer cold. And then the coils go behind your refrigerator where they condense. The vapor inside condenses, and so the heat gets released outside your refrigerator. So it doesn't make sense to open your refrigerator and hope that that cools down your apartment, because all of the heat that's getting taken out of the inside of your refrigerator is getting released outside your refrigerator. Okay, if you wanted that to work, you'd have to like put your refrigerator in the wall with the door open on the inside and the coils on the back of the refrigerator on the outside, and that's what we call an AC unit, in case you're interested. So all we want to know, though, is what mass of water could be converted to ice when this much CF4 evaporates. Well, I grabbed these equations from a couple videos ago. Let's pull these down and see how we can use them. Right? I know I want to use these because I have a situation where heat's being transferred from one thing into another thing. And this is handy for doing that. So what is the heat being transferred between? I've got Q of my CF4, and that's going to be negative Q of the water. Okay, my heat's being transferred between CF4 and water, or from the water to the CF4. Okay. Now I ask myself, do they give me any of these Q's? They don't. They don't tell me this much heat is absorbed or this much heat is released. Okay, so that means I want to break these Q's down into their component equation. So what's happening to the CF4? It's evaporating. Okay, well, my two options are I have a temperature change or I have a phase change reaction. In this case, if I'm evaporating, that's a phase change, so I'm going to replace the CF4, the QCF4 with N CF4 delta H CF4, which is negative. Then I ask what's happened to my water. My water is liquid converting to ice, so it's also a phase change. So I've got N water, delta H water. And which delta H? Well, it's freezing, so I'm going to use fusion is melting, so the delta H I'm going to use is going to be the negative delta H of fusion for water. And what's happening to my CF4? It's evaporating, so I'm going to use the delta H of vaporization of my CF4 if I want to get specific. All right, well, do I know these values? I do, so let's plug them in, and again, I'm trying to find how much water could be converted. So my amount is that moles of water. So they give me my delta H vaporization for CF4 in kilojoules per kilogram. That means that I want to use my N for CF4. I'm not going to use moles. I'm going to use kilograms because that's the amount unit in my delta H. So I'm going to have 0.1 kilograms of CF4, that's what came from here, times 136 kilojoules per kilogram equals negative. I'm looking for my amount of my water, and I need to use the delta H of fusion, the negative value of the delta H of fusion. Delta H of fusion is 6.01 kilojoules per mole, so then I'm going to use negative 6.01 kilojoules per mole. Okay, and I'm good. I got kilojoules on the left and kilojoules on the right. So when I solve for this, I'm going to get moles right here because this guy down there is moles. Okay, and when I did that, I got that N of my water equals 2.26 moles. But it wants to know the mass. And so what I've got to do is change this moles to mass, and that's as easy as multiplying by 18. So 18 grams in 1 mole of water. So my mass is going to be 40.7 grams of water. That's how much water I could freeze by evaporating 100 grams of my refrigerant CF4. All right, water in a leather flask or a porous clay pot can be cooled in hot climates by evaporating water from the surface of the container. Okay, so we've got a container, there's water inside, and I can make that water colder if I splash water on the outside which then evaporates. Why? If it wants to evaporate, it's got to take heat from somewhere. Since it's touching the pot, it's going to suck heat out of the pot, which is going to make the temperature of this water go down. All right, calculate what mass of water can be cooled from 35 to 20 via the evaporation of 60 grams of water. Okay, so I've got heat transferring between two different things here. So I've got the Q of the water, I'm going to call it the inside water, is going to equal negative Q of the outside water. What's happening to the inside water? Well, it is being cooled from 35 to 20 degrees. So I'm going to use an M inside, C inside, delta T inside, and it's going to equal negative Q outside. What's happening to the water outside? The water outside is evaporating. So I'm going to use an N outside, delta H vaporization outside. All right, so how much, so this is important to keep track of which variables go where. So this 60 grams of water, that is not the mass inside, right? That's the mass outside that's evaporating. So I can't put that for M there. What I'm actually looking for is the mass of the water that can be cooled. So I'm looking for the mass on the inside. It's liquid water, so I'm going to use a specific heat for liquid water, which is 4.184. My change in temperature is final minus initial. That has to equal negative. Do I have my amount of water on the outside? Yeah, it's 60 grams. And I'm going to go ahead and convert that 60 grams to moles because I know that my delta H of vaporization of water is given to me in moles. So that's 40.67. Okay, so we're almost there. The only problem we have is that on the left side of the equation we've got joules. On the right side of the equation we've got kilojoules. So I'm just going to jump in right here and say I know there's 1,000 joules in 1 kilojoule, and now I've taken care of that unit problem. So plugging all of this in, and to get this right, almost got it right. Mm, 16 divided by 18, 60 divided by 18 times 40.67 times 1,000 divided by 4.184 divided by 15. Okay, so I got that the mass inside is going to be equal to 2160 grams of water. That's how much water I could cool down from 35 to 20 by evaporating 60 grams of water on the outside. All right, next problem. In this problem, this big D should just say delta. It should be a delta. Just when I converted the PDF to text, it changed it to a D. Calculate the change in enthalpy for the reaction. For this reaction using these reactions. Okay, one thing I want to point out here, because we mentioned it earlier, we've got this naught value. That means that we're calculating this reaction at standard state. And that's fine because the component reactions are given at standard state, so we're good. Technically, if this said standard state and these were not at standard state, technically you might not be calculating the right thing, but we're not likely to give you a problem like that because you wouldn't be able to answer the question unless these were also all delta H naughts. Okay, so the idea here, this is Hess's law. The idea being if we can get these component reactions to add up to this reaction, then these delta H's will add up to this delta H. So why don't we go through how we would solve that. All right, I know that I have a C2H4 on the left, I'll try and be clean, on the left of the equation, the reaction. I don't have a C2H4 on the left here, I have one on the right. So what I'm going to do is I'm going to flip this bottom reaction. So that gives me C2H4 goes to 2C plus 2H2. Okay, so I don't care about this reaction anymore because because I flipped it. Well, the delta H of my new reaction is now the negative value of the original one. Because if the reaction going forward absorbs 52.3 kilojoules, then the reaction going backward must release 52.3 kilojoules. So I don't care about this anymore. I now have this reaction that I care about. And I've gotten my C2H4 on the left. All right, now I have 6F2 on the left. Here I've got 3. So I've got to multiply one of them by something. I don't know which one, though, so I'm not going to worry about that yet. Hopefully, cross my fingers that it fixes itself. So, not sure about that yet. I need 2 CF4s on the right side of the equation. I only have 1. So what can I do then? I can take this entire reaction and multiply it by 2. So I'm going to have 2 C's, I'm going to have 4 F2s, and I'm going to have 2 CF4s. The result is that the delta H of this reaction needs to get multiplied by 2. So then my delta H now equals negative 1360 kilojoules, and I don't care about this anymore. So now my 2 CF4s are taken care of. I need 4 HFs. I only have 2 HFs. So I need to do something similar here. Multiply this by 2, and this is now 4. And this delta H becomes negative 1074. That looks right. And I don't care about this anymore. So now the question is, do my 3 reactions now add up to my total reaction? Okay. Well, this isn't how I normally do it, but I'll write it out this way because maybe it'll help. I'm going to write all of my reactants and all of my products in one line. So I've got 2H2 plus 2F2 plus 2 carbon plus 4F2 plus C2H4. So that's all of my reactants. And those go to 4HF plus 2CF4 plus 2C plus 2H2 for all of my products. And now I can go through and say, well, I have 2 H2s on the left and 2 H2s on the right, 2 carbons on the left, 2 carbons on the right. These F's can combine, and I get 6F2 plus C2H4 goes to 4HF plus 2CF4. And you should notice that is my original reaction that I'm trying to get to. So I've confirmed that these 3 reactions add up to this reaction. So if I want the delta H for this reaction, I can add up the delta H's for the component reactions. So this is, I'll write it over here. Whoa. So then I can say delta H naught is going to be negative 1074 minus 1360 minus 52.3. And that gives me 2486.3. Hopefully that is correct. Yep, looks like it is. So the delta H naught of this reaction is negative 2468.3 kilojoules. All right, that is a Hess's Law problem. All right, now let's look at number 8. The enthalpy of combustion for graphite is negative 393.5 kilojoules per mole. The enthalpy of combustion for diamond is negative 395.4 kilojoules per mole. Use this information and Hess's Law to calculate delta H of reaction for converting diamond into graphite. This is endo or exothermic. All right, they tell me to use Hess's Law, but they don't give me component reactions. They do, however, they give me the delta H of combustion for graphite and for diamond. So what I'm going to do is I'm going to write out the combustion reactions for graphite and for diamond. So combustion, if you remember, let's see, graphite and diamond are both just carbon. So I'm going to write Cg and Cd for carbon graphite and carbon diamond. Combustion is just adding oxygen and making CO2. If you add hydrogen in the thing you're burning, you also get H2O. And specifically, if I'm writing a combustion reaction, I've got to burn exactly 1 mole, and so the delta H for this reaction is negative 393.5 kilojoules per mole of carbon. Then I've got the combustion of diamond. C diamond plus O2 goes to CO2, and that delta H is equal to negative 395.4 kilojoules. And what am I trying to calculate the delta H of? The conversion of diamond into graphite. So literally, C diamond goes to C graphite. That is what I am trying to find the delta H of. They tell me to use Hess's law. Well, I've got diamond on the left, so that's good. Graphite on the right, but my graphite is on the left, so I'm going to switch that equation. I'm going to get CO2 goes to C graphite plus O2, and now the delta H of that reaction is just the inverse value or the negative value of the original one. So I don't care about this reaction anymore. I've gotten the one I want. So now my carbon graphite's on the right. I have the carbon diamonds on the left, and you can see CO2 cancels and O2 cancels, which means I've got C diamond goes to C graphite, which is what I want. So the delta H is going to equal negative 395.4 plus 393.5, and that gives me a value of negative 1.9 kilojoules. So the delta H of converting diamond into graphite equals negative 1.9 kilojoules. So endo or exo, it's negative, so this is exothermic. So this problem is a Hess's law problem, but it required you to write the reactions, meaning that you need to understand when they said combustion of graphite, the enthalpy for combustion of graphite is negative 393.5 kilojoules per mole. You needed to know that that was referring, that's just the delta H of the combustion reaction. So the enthalpy of combustion, that's just the delta H of the combustion reaction. So if I can write the combustion reaction, then I know the delta H of that reaction. That's what I did here, and I was able to use Hess's law to calculate the delta H and figure out if this process was endothermic or exothermic. So essentially when diamond converts into graphite, heat's released, which makes sense because we know that if we want to convert graphite into diamond, it takes a lot of pressure and a lot of temperature. All right, so that brings us to the end of problem set 35 about enthalpy, and we'll call it a day.